Hi everyone, welcome to another video. We're going to continue exploring these logarithms in this video, like we did previously, but what we're going to do now is look at how we would graph something like this. And like with a lot of my other videos, I don't want to jump straight into showing you the exact graph. We want to investigate it a little bit. So before we do anything, I'm going to give you just a simple form of a logarithm equation. So I've got here y equals to log to the base 2 of x. So this is like a graph that you may encounter sometime in the next few videos. So this guy here, this is currently in log form. So in order to actually understand what is happening here, we want to make this something that might be familiar to us. So we're going to consider a few things. So we have the base over here, we have our power over here, if we remember from the previous videos, and we have we call that our answer over here. So if we wanted to write this, for example, in exponential form, we're going to change this up a little bit. And we learned from the last video that we can write this as my base 2 to the power of y, because this is my power over here, my base is the 2, equals to x. So all I've done here is I've just rearranged. So my answer goes over here, my power goes up here, and my base goes over here. So I've just rearranged this from log form to exponential form. Now let's actually look at what this thing actually resembles. Now it looks very similar to some of the other exponentials we dealt with in previous video series. This actually resembles a function that we talked about before, this guy y equals 2 to the power of x. Now, if we remember this guy here, let's draw a nice red box around it. This resembles my thing that I wrote up here in exponential form, but there's one difference. So the exponentials we observed previously, the y and the x here have swapped places. So when we actually drew this thing here, we had, let's leave it in red, we had a function that looks like this, and it shoots up. It has a y-intercept at 1, and we notice that as it continues down this way, it approaches 0. It has what we call an asymptote at, let's do this in green, has an asymptote at y equals to 0. Now, this guy that I've drawn in red is different to my thing up here. I just left this here just temporarily, this graph of y equals 2 to the power of x, because we now want to investigate this thing up here. So my log equation here, written in exponential form, this guy with a green box around it, 2 to the power of y equals to x. So just momentarily, let's just write this down here. So x equals to 2 to the power of y. Like with a lot of graphs when we don't actually know what's going on, we're going to write up a table of values. So I'm going to draw this thing here, and we're going to try to explore what's actually going on here. So let's just pop in, because here I'm going to substitute because my x is the subject of the equation, let's just substitute in a couple of different y values to see what x I'm going to get. So let's say I go from, on the y's, let's go -3, -2, -1, 0, 1, and 2. So let's pop this in. I'm going to substitute each of these y values into up here. So first, x equals 2 to the power of negative 3, that's going to be the same as 1 over 8. If I substitute in negative 2 into this y, I'm going to get 1 over 4. Whoops. 1 over 4. Here I'm going to get a half. Here I'm going to get 1, 2, and 4. You guys can pause this and have a go at this on your own, but by now we should be pretty comfortable with substituting into a table of values. The only difference here was I just substituted in a few y values in order to get my x output, which is the subject of the equation. So let's actually go ahead and on here we're going to graph those, we're going to plot, those different points. So the first one is that when y equals to negative 3, so let's say down here, y equals negative 3, so let's say this is the point 1, 2, 3, and we have negative 3, negative 2, negative 1. When y equals to negative 3, so down here, x is going to be 1/8, so that's going to be about here. So very, very close. I'll put that in there. Let's actually do this in a different color. So that's going to be about here. Okay, when y equals to negative 2, x is going to be about 1/4, so something like this. When y equals negative 1, x is going to be about 1/2, so that's about here. Sorry everyone, the thing is bugging out a little bit, but that's okay. When, let's draw it maybe closer to here. Alright, when y equals to 0, x equals to 1. When y equals to 1, x equals to 2. That's about here. And when y equals to 2, x equals to 4. So that's about there. Okay, so keep in mind, this thing x equals 2 to the power of y, that is exactly the same as y equals to log to the base 2 of x. So I'm essentially graphing this guy down here. We're trying to find just a general way to plot and graph a basic log function. So now that I've got all of these points, I'm going to draw a line connecting each of these, and I get something looking like this, where I get my function y equals to log to the base 2 of x. Now, let's just make a couple of observations. For one, I can see that for smaller values of y, so as my y keeps going down here, my x is going to get smaller. So let's actually move this down. Couple of things I notice is that as y values get smaller, the x values, well, what are they going to approach? Well, we notice a pattern here that as we keep going across here, in this direction, on the y values, my x values are halving. They go from 4 to 2 to 1 to half to 1/4 to 1/8, then to 1/16. So my x value will approach 0. 0. In the same way that as my x values got smaller on my exponential, my y approached 0. So we can say over here, down the bottom, as y gets smaller, my x value approaches to 0. So I can say over here, it looks like this is getting really, really close to the y-axis, but never touching it. We're getting this fraction thing happening again. So we have that an asymptote. We have an asymptote at x equals to 0. Because it's never going to reach a value of 0 for x. It's just going to keep halving and halving and halving. So if we look at this, we can kind of see these graphs are sort of opposites to one another. My graph here, my y equals 2 to the power of x, it starts off increasing slowly and then it shoots up after this point. Whereas my log graph, it shoots up to start off with and then it slows down. So we can see a kind of opposite relationship between these graphs. Another thing we notice is that, well, there is an x-intercept at 1. So for my exponential graph, I had a y-intercept of 1. Here I have an x-intercept of 1. Actually, let's just leave it like that. So I have an x-intercept at 1, whereas on my exponential graph I had a y-intercept at 1. So we can notice a few things. There is a kind of opposite relationship happening between this graph that we're more familiar with, y equals any exponential 2 to the power of x, that we did in a previous series. And with my log, my y equals to log to the base 2 of x, we can rewrite that in exponential form as x equals 2 to the power of y, in which the x and the y are flipped over, they change positions from over here. And the graphs actually look like they're opposite in every way. One of them has, when one is the x-intercept of 1, the other has a y-intercept of 1. When one has an asymptote at y equals to 0, the other has an asymptote at x equals to 0. As one starts off slowly and shoots up quickly, the other starts off quickly and then shoots up slowly. Now, some of you may have already had an idea of what I'm getting at here through this idea of opposites, but let's just draw something to revisit a pretty significant concept. Now, let's do this in like a dark green color. If I draw in a line here, and this is a line that is y equals to x, does it look like one is sort of like a mirror image of the other one? Now, if you guys sort of tilt your head 45 degrees so that you can, this green line is perfectly vertical, you can see this mirror reflection happening. Also, if you want to turn your head even further and look at this graph, it looks like an exponential just with the x and y's flipped over, which is exactly what we discovered down here. Now, this is the big kind of idea that I am getting at here. Some graph y equals to log to the base 2 of x, and a different graph y equals 2 to the power of x, these are inverse functions. So my log graph is with the same base of 2 is the inverse to this particular graph. It meets the criteria. All the x and y characteristics are flipped over. And when we draw this line y equals to x on my little plane that I've got here, we can see a pretty perfect mirror reflection happening between our two graphs. So there is a logarithmic, well, this logarithm that we talked about, it has a very inherent relationship with my exponential. It is its inverse. And we get to this by considering exponential and log form. So once we know about the exponentials, it can tell us a lot about the logs. But the basic shape for a logarithm, this one has a base of 2. This is going to be something that looks like this. So my general log, just to conclude for this bit, and we'll talk about this a lot more in detail, but we're just investigating this concept. My general log of the form y equals log to some base a of x, where a is greater than 1, it's going to look somewhat like, that's not a good drawing, something like this, where it has an intercept of 1 and it has an asymptote at x equals to 0. So as the y gets smaller down here, my x value will approach 0. So this is the general form and sort of shape and how this will look. And in the next few videos, we will look at some transformations of these log functions and how this can basically change. But we can pretty much see that this has an inverse relationship with my exponential of the form y equals a to the power of x. When reflected here along the line y equals x, we can see the inverse relationship between those two. But this is what the basic log graph looks like, and we will investigate this a lot more in the next few videos. But thank you so much for joining me today, and I'll see you next time.